Now that you can identify redox reactions, let's talk about how to balance them. It is a little more complicated than balancing other types of reactions, and you can even see the preview now, you will need to go through some specific steps in order to balance these properly and without crying and having a really bad time. Now, this is also why the combustion reactions that we learned how to balance a while ago have to be balanced in a specific order. Combustion reactions are redox reactions. They are just non-aqueous redox reactions. This method is going to work for everything that is an aqueous redox reaction. We're going to use the half reaction method. Please use the half reaction method and not the method that is given in the OpenStax textbook if you are referencing that. So in the half reaction method, the first step is to assign oxidation numbers to determine what is oxidized and reduced. Second, we will separate into oxidation half reactions and reduction half reactions. So the stuff that gets oxidized, pull it out. The stuff that gets reduced, put it to the other side, and then each half reaction will be balanced separately, and then we'll put them back together. For each half reaction, you will first balance all of the elements except oxygen and hydrogen, then balance the number of electrons gained or lost, then balance the net charges. This is where you will need to know if the reaction is happening in an acidic solution, which means you can use H plus to balance the charges, or in a basic solution, which is when you would use OH minus to balance the charges. Then you'll balance oxygen and hydrogen with water, and this will be a really good checkpoint. If you cannot perfectly make a specific number of whole water molecules, then something went wrong. After this, for each half reaction, you'll make the number of electrons gained equal the number lost, which is going to mean multiplying through by some coefficients so that you have the same number of electrons in each half reaction, and then you add the half reactions together. Now, the goal from 4 to 5 is that the electrons cancel out, which is why in the final version of the redox reactions, we don't see any electrons. It's kind of hidden that those electrons moved, but they did move, which is why it's a redox reaction. Okay, our first example is a reaction taking place in an acidic solution. We are given that MnO4-, which is permanganate, is reacting with bromide, and our result is manganese 4 oxide and bromate. So, this looks like it's definitely going to be a redox reaction, and it's an example in the How to Balance Redox Reactions video, so good chance that it is redox. But let's start by assigning all of our oxidation numbers. In permanganate, the oxygen is the only thing we have a rule for. So permanganate, the oxygen will get a -2. This means that manganese must have a +7. Bromide, the bromine gets a -1. In manganese 4 oxide, which you might get a little hint there since it's an ionic compound, we only have a rule for oxygen. It gets a -2. That leaves manganese with a +4. And in bromate, the oxygen, we have a rule for both, but the oxygen rule comes first. So we assign oxygen a -2, and that means that bromine must have a +5 in this reaction. So to answer the question, what changed? Well, our manganese went from +7 to +4. That is gaining electrons, so manganese was reduced. Bromine went from +1 to +5. It lost electrons, which means bromine was oxidized. The next step is to split this up into half reactions. that means that I will take the thing being reduced. So manganese was reduced. So I can't take manganese out of its polyatomic ion. So I just take the whole thing, MnO4 minus, and then the product is going to be anything from the product side that had manganese in it. So my half reaction for reduction is the permanganate turning into manganese 4 oxide. The oxidation reaction is, well, everything that's left over, or finding what was oxidized. And it's the bromine. I started out with bromide, and it turned into bromate. So that is my oxidation half reaction. The next step is to balance each half reaction on its own. So starting with the oxidation half reaction, and it doesn't matter which one you start with, I just happen to start with this one. I have Br minus turning into BrO3 minus. So the first thing I balance is all of the elements except for oxygen and hydrogen. Well, for this, that means bromine. So I have one bromine on each side, and that's it. That's all I have to do for that step. I'm done. The next step is to balance the number of electrons gained or lost. So this is oxidation, which means losing electrons. And my bromine went from a -1 to a +5. So it lost 6 electrons. Now, the thing is, like, you can't write Br minus minus 6 electrons. It would be the easiest way to say that something lost electrons, but by convention, we only use plus signs in reactions. So what that means is that I'm going to put those 6 electrons on the product side. So Br minus turning into BrO3 minus plus 6 electrons. The next step is to balance the net charges. So what this means is take everything on the left side and add up all the charges. Well, I mean, we're a little pitiful here at the moment. I've just got Br minus. The total charge on the left-hand side is -1. On the right-hand side, I have 6 electrons and a bromate. That's a total charge of -7. I want to make the two sides equal each other. They don't have to equal 0. They just have to equal each other. And this is in acidic solution based on what I was given at the beginning. So the only thing I can do is add H plus to this solution or to this reaction to get the charges to balance. That means I am stuck. I have to add it to the right-hand side. And if I add 6H plus, I can check my overall charges again and see what comes out. So I still have a -1 on the left, but now I have a -1 from the bromate, I have 6 negatives from the electrons, and 6 pluses from the H plus. So I have a -1 charge on both sides. That's what that step means. Now I can balance oxygen and hydrogen by adding water. Now I currently don't have any oxygens or hydrogens on the left, so that's where I'm going to end up adding my waters. On the right-hand side, I have 3 oxygens and conveniently 6 hydrogens, which perfectly makes 3 molecules of water. So this is what I mean when I say that you should be able to get a perfect number of water molecules when you go to do this step. Okay, so my balanced oxidation half reaction is 3 waters plus 1 bromide turning into a bromate, 6 electrons, and 6 H pluses. Now I need to balance the reduction half reaction. So I've got permanganate turning into manganese 4 oxide. Balancing elements other than oxygen and hydrogen, manganese is the only thing, and I have 1 on each side. To go from a +7 to a +4, my manganese needed to gain 3 electrons. So gaining electrons, those electrons are going to be on the reactant side. So MnO4 minus plus 3 electrons, turning into MnO2. When I add up the charges, on the left side, I have 3 electrons and a polyatomic anion with a -1 charge. That's a total of -4. And on the right, I just have a neutral compound, so that's a 0. So where I am currently is -4, 0. I can only add H pluses. So I'm going to add my H pluses to the reactant side. And that puts me at permanganate plus 3 electrons plus 4 H pluses, turning into MnO2. 0 charge on both sides. And for balancing oxygen and hydrogen with water, on the left, I have 4 oxygens and 4 hydrogens. Now that will not perfectly make a number of water molecules. With 4 hydrogens, the best I can do is 2 water molecules, but MnO2 already has 2 oxygens. So if I put 2 water molecules on the right side, I'm perfectly done. Okay, so my reduction half reaction is permanganate plus 3 electrons plus 4H plus, turning into manganese 4 oxide plus 2 H2O. The next step is to make the number of electrons gained equal the number of electrons lost. So I've rewritten my 2 half reactions. In the oxidation half reaction, I have 6 electrons being transferred. In the reduction half reaction, I have 3 electrons being transferred. If I multiply my reduction half reaction by 2, that will give me 6 electrons in that reaction, so that when I add them together, my electrons perfectly cancel out. Now, the great thing here about this step and the next step is that chemical reactions, you can treat them just like algebra equations. So when I multiply through by 2, I'm just going to multiply all the coefficients. And where that leaves me is my first reaction is the same, the 3H2O plus Br minus, making BrO3 minus, 6 electrons and 6H plus. And then my bottom reaction is 2 MnO4 minus plus 6 electrons plus 8H plus, making 2 MnO2 and 4 waters. When I add them together and cancel out things that appear on both sides, my result is 2 MnO4 minus plus Br minus plus 2H plus, turning into BrO3 minus plus 2 MnO2 minus plus H2O.